Welcome to today's tutorial. Today we are going to speak about eigenvalues and eigenvectors. So at first, let's look into the definition of eigenvalue and eigenvector. Here we have an n-to-n matrix A, and then we have a real number lambda, which is called an eigenvalue of A if there exists a non-zero vector V, which is an element of real numbers in any dimension, such that the matrix A times the non-zero vector V will be equal to the eigenvalue lambda, which is any real number, times the vector V. So in this case, the vector V is called an eigenvector of the matrix A corresponding to the eigenvalue lambda. So here, the vector V is the eigenvector of matrix A, which is corresponding to the eigenvalue lambda. Okay, and the vector V, the eigenvector V, is a non-zero vector. So its elements are not equal to 0. It is not a zero vector. So let's look into an example for this. Let A be a 2 by 2 matrix here. So let's say A is equal to A, B, C, and D. In that case, the vector V, which is x1, x2, is not equal to, or you can say which is a non-zero vector. So here, if lambda is the eigenvalue of A, then A times V, the matrix A times the eigenvector V, is equal to lambda, the eigenvalue, times the non-zero eigenvector V. So that is, if we write in the matrix form, so we have the matrix A, B, C, D times the eigenvector x1, x2 is equal to some real number lambda, which is an eigenvalue of the matrix corresponding to the eigenvector x1, x2. So that would be the definition of eigenvalues and eigenvectors. Now let's start the task for today, which is a proof of a statement. So here we have a statement given to us, which is if you have two eigenvectors to two different eigenvalues, they cannot be on the same line. So maybe to explain this in more detail, let me write it down here. So if the vector x comma y, or xy, is an eigenvector of the matrix A, B, C, D corresponding to the eigenvalue lambda is equal to 3, and if we have one more vector mn, which is an eigenvector of the matrix A, B, C, D corresponding to the eigenvalue lambda is equal to 5, in that case, the two eigenvectors x, y, and mn are not on the same line. They cannot be on the same line. That's what the statement is saying us. If we have two eigenvectors, just like we have here x, y, and mn, to two different eigenvalues. So for the eigenvalue of xy is 3 here, and the eigenvalue for mn is 5. So they cannot be on the same line. Now, let's look into what does this statement mean by definition here. The statements that we have written. So what does it mean here is that the matrix A, B, C, D times the eigenvector xy is equal to the eigenvalue 3 times the eigenvector xy. So that's by definition here, and here also it means A, B, C, D times mn is equal to 5 times mn. And as per our statement, what it says is that, so graphically if I show you, it says that if here you have x and y, and you have the vector xy here, let's say here we have x, y, and then this side here we have the vector mn. So as you can see, these two vectors are not on the same line, because if it has to be on the same line, which is if it has to be on this line here, then it has to be some number, some real numbers, let's say lambda, times the vector xy, right? So what does this actually mean, or what does the statement actually mean here? It means that the vector or eigenvector xy is not equal to, so it's not equal to any real number times the vector mn. So that's what it means by it's not on the same line. The two vectors to two different eigenvalues are not on the same line, and if you write that down, it would look like this one here, which is that vector xy is not on the same line with vector mn, so it's not equal to any real number times the vector mn. Now, how can we prove this statement here? How can we prove the statement that we have here? What we can do is that we can assume that the two vectors xy and mn are on the same line. We can assume that this statement here is true. And if we assume that it is true, then we will get the contradiction. So let's go ahead and do that. So let's assume that the vector xy is equal to some real number times the vector mn. So here, if that is true, in that case x will be equal to some real number times m, and y will be equal to some real number times n, right? So that would mean this here. Now, if you have the matrix A, B, C, D times the eigenvector xy, this would be equal to, so here I'm keeping the matrix same, A, B, C, D, and that will be, or you can say I'll replace the xy with what we have got here. Some real number times m is x and some real number times n is y. So that's what we'll replace here with. Now this here, you can say is equal to, if you take out the real number as common out, so here you will have some real number times the vector mn, and now if you put the real number inside the bracket and if you solve this and factor it out, you will get here the real number times A, B, C, D times m n. Okay, now we know that the real number times mn is actually equal to, so here from the definition, from here we know that the real number times mn is equal to 5 times mn, right? The eigenvalue times the eigenvector. So we can say that here the real number times 5 times mn. Now putting in the real number inside the vector again, you will get here 5 times the real number times m, here and here the real number times n. So according to this definition here that we have seen, so here we can write this as 5 times real number m can be replaced by x and real number times n can be replaced by y. Okay, now if you look into this one here, what does this mean? Again, by the definition, it means that the matrix A, B, C, D times xy is actually equal to 3 times xy. So this here is actually equal to 3 times x comma y, and that is equal to, we are saying 5 times x comma y. So what we're saying is that 5 times x comma y and 3 times x comma y are equal to each other, which is not possible. That's a contradiction. And that proves that it's not, the two vectors to two different eigenvalues are not on the same line. And thus our statement is true, which says that if you have two eigenvectors to two different eigenvalues, they cannot be on the same line. Now let's take an example that proves the statement that we just discussed. So let's consider the 2 by 2 matrix, which is 2, 1, 4, minus 1, whose eigenvalues are 3 and minus 2, and their corresponding eigenvectors are r and r minus 4r. So what does this show here is that if you have the, let's take the matrix that is 2, 1, 4, minus 1 here, and if we multiply to the eigenvector r, we get here 2r plus r, and then we get here 4r minus r, and that is equal to 3r and 3r. where if you take out 3 as common, you get here RR. So here we have the eigenvalue and the eigenvector, and here R could be any number or all real numbers except equal to 0, because if it is equal to 0, it would make it a 0 vector here, and eigenvector is a non-zero vector. And then now if you take the matrix 2, 1, 4, minus 1 with the second vector, which is R minus 4R here, it would result in 2R minus 4R, and then we would have 4R plus 4R. This here is equal to minus 2R and 8R. And if we take out minus 2 common, we get here R and minus 4R, which is our second eigenvector and second eigenvalue, again where R is not equal to 0. Okay, so as we discussed in our statement, it says that the vector, here we have two eigenvectors to two different eigenvalues, and they cannot be on the same line, which would mean that if R, the vector RR is not equal to any real number multiple of the vector R times minus 4R. Now let me make this more simple using numbers. So here, instead of RR, let's consider the numbers 3, 3. So that we want to say that it is equal to some numbers. Let's say here we take for R1. So here we'll have 1 and minus 4. So we need to multiply some number here, that if we multiply to this vector 1 minus 4, we will get RR. So here we know if we multiply 3, then at the top we get 3 is equal to 3 times 1, which is 3. But below we get 3 is equal to 3 times minus 4, which is minus 12. So that's not true. So they are not equal. We could also try with taking any other real numbers, like let's say 7, 7. And then we want a real number where we want to get here, let's say 2. So R is equal to 2. So here we'll have minus 8. And we want some number where we'll get this both equal, and that's also not possible. So this is again showing you that, or this proves that any two eigenvectors to two different eigenvalues are not on the same line. That's not possible, right? Also, we could say it like, if we have two different eigenvectors to the same eigenvalue, then they are on the same line. Okay, so what we're saying here is that if we have two different eigenvectors to the same eigenvalue, then they are on the same line. So let's say we are now looking at the eigenvectors RR. So let's take two different eigenvectors. One is, let's take 1, 1, and other one we would take here as 3, 3. And our eigenvalue for RR was 3. So these both are on the same line. So if we have two different eigenvectors to the same eigenvalue, they are on the same line. So here, if we draw it graphically, we will have 3 times 1, 1 would be equal to, let's say, 3, 3. So that's 3 here and 3 here. So that's the one. And then 3 times 3, 3 is 9, 9. So that would be again on the line x is equal to y at 9, 9 here. Right? So they are on the same line. Maybe we can also take the other vector example, which is r and minus 4r. So if we take two vectors, let's say 1 and minus 4 here, and then here we will take the vector 2 and minus 8, and then we have the eigenvalue for this vector here is minus 2. So they will be equal to minus 2, 8 here, and that would be equal to minus 4 and 16. So they both are also on the same line if you draw and see graphically. Now we have one more statement which is true, that is two eigenvalues to the same eigenvector are on the same line. So here if you have two eigenvalues, that means two different eigenvalues to the same eigenvector are on the same line. So let's say you have the same eigenvector. Let's consider eigenvector maybe 2 and 3. So if you have two different eigenvalues, that could be 2 times 2, 3. So the eigenvalue here is 2. Or you could take here, maybe I'll write it above here. So you could take maybe 3 times 2, 3. So as you know, they are multiple of the same vector. So they're of course on the same line, right? So this would be 6, 9. And that would be 4, 6. So they are on the same line because they are just a single line. So here you have 6, 9, which will be, let's say, somewhere here. And then you have 4, 6, which will be somewhere here. So yeah, they'll be on the same line because they are just multiple on the line 2, 3 on the vector. You can say here, if I draw it a little bit neatly, so let's say you have the vector 2, 3, which is around here. So this is your vector, and this would be the line of the vector. So anywhere on it, you have either, so here you have 2, 3. So if you have 2 times 2, 3, it would be maybe here. 2 times 2, 3, and 3 times 2, 3 will be somewhere here. And if you have a negative number multiplied to it, let's say minus 1, then it would be somewhere here maybe. So you will have minus 1 times 2, 3. So if we have different eigenvalues to the same eigenvector, they are also on the same line, right? But as we have proved initially, if we have two different eigenvalues to two different eigenvectors, or you can say if we have two different eigenvectors to two different eigenvalues, they cannot be on the same line. And that's the end of today's tutorial.